Let's see.
It was supposed to.
Okay, there we go. I turned it off.
All right, thank you for that. Sorry about that.
Yeah, no problem. Okay, so yes, exactly. Welcome everybody to the Quantum Matter seminars hosted at Northeastern University. Today we have our guest is Maria Rey from NIST, and she'll be talking about dynamics of interacting fermions with spin orbit coupling. So this, as in with previous weeks, we'll actually, Anna, do you think that there's any spots where you might want to stop for questions, or do you think we can just wait until the end?
Well, I can stop at the middle. Yes, I can have a place that I can stop and I can, yes, that could be good. Yes, in the kind of interview to talk.
All right, so when you're ready, just let me know and then we'll stop for questions. And then, so, you know, if you have to, or if you want to ask your question in the chat, go ahead and just type it into the chat and then we'll read those off. And otherwise you can raise your hand and we will unmute you and you can address your questions directly. And with that, go ahead and get started.
Okay, thank you very much for the invitation. It is a great pleasure to speak at the Quantum Matter seminar. Well, it's again an online talk, so it's a little bit different to what I'm used to, but hopefully, well, we can all learn what I'm going to tell you about today. That is the topic of dynamics of interacting fermions under spin orbit coupling. And the basic idea here is we want to study spin orbit coupling, but until the context that it can allow us new tools to understand the behavior of driven many-body systems and can help us to actually enhance coherence and generate entanglement with applications relevant for quantum technologies. That's kind of our overall goal. And I'm going to start this talk by acknowledging the people who actually did all the calculations that I'm going to discuss today. It's my group of graduate students and postdoc, and in particular, I want to highlight the work of Michael Mamaev, Peiruhi, Michael Perlin, and there was a prior postdoc in my group, Michael Wolf, who did all the calculations, and all, well, of course, there are more people that contributed heavily to the work that I'm going to discuss. And this work has been done in very close collaboration with Junji Optical Lattice Cloc at GILA. So all the data that I'm going to talk about and many of the work has been done in collaboration with his group of graduate students and postdocs, and I have highlighted some of the names of the people who took most of the measurements. All right, so I want to start with a scientific vision of my work that is trying to understand how we can harness and control quantum many-body systems and use them for applications that are useful for quantum technologies, ranging from quantum information to metrology. And of course, the issue is that many-body systems are complicated, but what the question that we want to understand is how complex behaviors can emerge from simple constituents and their interactions. So trying to bridge the gap between the few body to the many body. And here, the tools that we want to take advantage is the tools that atomic, molecular, and optical systems offer to us. And in particular, I want to emphasize that these systems allow us to understand the microscopic behavior very well. So basically, we can take a piece of paper and write the Hamiltonian explicitly. And this is exactly the Hamiltonian that is ruling the behavior of the system. I can, moreover, tune the interactions of my Hamiltonian almost in real time and access dynamics at also accessible time scales that doesn't need, for example, ultra-fast probes. And well, what is the vision? The vision is that we want to use these that can become correlated on anybody for different applications that are very relevant for us. On one hand, we have to build and construct synthetic quantum materials that allow us to perform quantum simulators and shed light, for example, in the behavior on complex behavior that we don't understand yet. For example, we want to understand the origin of high temperature superconductivity. The other direction that we would like to use these systems is actually to quantum computers and trying to make this very powerful device that has great promise, but they're really challenging to build. So in this talk, I'm going to touch base on first very basic ideas on how we can go towards this direction, and the wall of quantum supremacy. Finally, or another, this direction is trying to use these systems that are fully controllable and we can measure very precisely to understand fundamental physics. We see connections that have been pointed, for example, from quantum gravity, understanding the behavior of black holes and dark matter that might be very different to what we can access in ultra-atomic systems, but nevertheless, there has been connections that says that unitary systems maybe have similar behavior through the evolution of quantum entanglement to these systems. And of course, and at the heart of my research interest is try to build a very precise sensors where we are using many body quantum correlations for advanced metrology. So basically we want to create sensors that have highest accuracy at the height. And interestingly, all these four goals that are really, really challenging, but really well, a very important milestone for the community, can be all being principle implemented through the use of the new generation of 3D optical lattice clocks. So I think these systems open a path, open a window to actually accomplish all of these very interesting goals. So I want to start by discussing a little bit about the clocks, and then start to jump that with the behavior of fermionic systems in a lattice. So the new generation of optical lattice clocks that we are talking about are operating with neutral atoms. And in particular, we are interested in the atoms that are alkaline air atoms. As you might remember, these are atoms that are in the second column of the periodic table. And our element today is going to be strontium. So this strontium has a unique atomic structure due to these two outer electrons. It offers the possibility of having the ground state of the system and a metastable state, an electronic state. This is the 3p0 state if you are interested. But the important part is that this transition is extremely long-lived. So this transition is spin and dipole forbidden, and that means that atoms in the excited state can have a lifetime that is longer than 100 seconds, meaning that we can have very, very precise resolution, spectral resolution, with a line width that is below of the order of millihertz. So with this type of systems, actually June and his team at GILA have been able to build a clock that has record levels of precision and accuracy, that as precise as an uncertainty, total uncertainty of 10 to the, at the level of 10 to the minus 18. Maybe in order to put a little bit of context of how good is this clock, is imagine a clock that never gains or lose 1 second during a kind of 15 billion years, roughly the age of the universe. So that's the level of precision that these clocks brings to us. That is incredible. And maybe you are sitting there and you're asking why we care for many body physics about this precision. And I will start with a very simple cartoon trying to convey the message why these clocks are useful. And well, it is the following. So imagine that you are a regular clock of a bad clock, and you are only coherent for very short time. So you don't have this very long lifetime that the GILA clock has. So I'm going to ask you, what do you see? Okay, I'm going to ask you one more time. What do you see? Let's see. No, sorry. This animation, sorry. Okay, what do you see? Now imagine that you are a good clock, the good optical lattice clock at GILA. Okay, let's see one more time. What do you see? So I hope, for maybe these animations are not that good in online, but I hope you could see that in the second part, when you have long probing time, you could see clearly that there was a hydrogen atom, whereas in the short time, it was very blurry. So that's the idea of what we want to accomplish with optical, very good clocks. So we want to get a marriage between the precision and the exquisite sensitivity of an optical lattice clock in order to probe many body systems and resolve a very broad many body spectrum into very well resolved lines that allow us to understand the behavior of many body systems. That's the goal. And we think that with ultra cold atoms at the clock, that the new generation of optical lattice clock at GILA, we can accomplish that. Now, the atoms, the type of atoms that we are using is really important. And the reason is that if I ask you to think, what are the key ingredients that strongly correlated materials have in solid state systems? Maybe you could tell me that is the intrinsic and complicated interplay between charge, orbital, and spin degrees of freedom. This is what makes the description of the systems very complicated. The good news is that in a single atom, the strontium atom, we are able to encode all these degrees of freedom at the same time. Basically, we have an orbital degrees of freedom because we have the two clock states that are very long-lived that I told you just in a few minutes ago. Then it happens that in additional strontium, the fermionic isotope has a nuclear spin structure, have 10 nuclear internal levels that we can take use to, so we can encode their nuclear spin degrees of freedom. This part is not going to emphasize very much, but this is another opportunity that we have. And finally, even though we cannot have charged particles, what I'm going to tell you now is that we can make these atoms through lasers behave as charged electron and exhibits the analog of spin orbit coupling, or what is called also synthetic H field. So this is going to be at the heart of my talk today. This interplay between orbital and charged degree of freedoms. So a little bit more of why is now the time to explore this rich physics is because now the optical lattice clock at GILA have really improved significantly, and we have the new generation consists of ultra cold quantum degenerated gas of fermionic strontium atoms that are cooled down and trapped in a 3D optical lattice. An lattice emulates a periodic potential similar to the periodic potential that electrons feels in solids. So in this new clock, he has been able to interrogate to have of the order of 10 to the 5 atoms and cool them down to temperatures that is of the order of 0.1 times the Fermi energy, or the Fermi temperature. So it's really, really quantum degenerate, very cold, all the degrees of freedom at the quantum level. And in these systems, he has been able to reach coherence times that of the order of 12 seconds, that are the coherence times that are longer than the typical energy scales that we need to use in the lattice, so opening great opportunities. So moreover, at least initially, the hope of these clocks was to pack as many atoms without being immune to collisions that typically in 1D optical lattice clock used to be a very detrimental effect. So in this talk, I'm going to tell you a little bit about how in principle you can turn off interactions in these clocks, but more importantly, if you harness them, you can have great advantage. So that's going to be at the heart of this talk today. So going back to the physics of electrons in a periodic potential, they are described by the so-called Hubbard model. That is one of the simplest models that describe magnetism of strongly correlated systems. In this case, we are going to have a nuclear spin polarized gas, and the spin degree of freedom is going to be encoded in the clock states. So the ground and the 1s0 and the 0 states are going to encode the spin 1/2 degrees of freedom. And the dynamics of ultra-cold atoms in the lattice when they're in the lowest band is described by a tunneling term that is parameterized by J, that is nearest neighbor tunneling between different nearest neighbor lattice sites, and an interaction energy U, that is the energy cost of having two atoms in the same lattice site, and because they're fermions, of course, they have to be in a singlet configuration. All right, so you can see that because the tunneling, it can be exponentially suppressed as you make the lattice deeper and deeper, because it's quantum tunneling. Then in principle, if you are able to actually load the atoms with one atom per site or use strong interactions to prevent multiple occupancy, then we can have a clock that have one atom per lattice side without tunneling, no collisions. So it's the ideal scenario for having a clock where you can pack many atoms without undesired effects from tunneling or interactions. So in principle, that was the first idea that Jung had. But of course, then complications come, and the complications, as you could imagine, I mean, of course, he knew that there could be this type of problems, is that if you start to trap the atoms in a very strong potential, like in 3D lattice, you start to suffer from tensor and vectorial star shifts from the lattice beam. But most importantly, he has seen that the lifetime of the excited state is significantly shortened by light scattering. So now the lifetime that's what mainly limits the lifetime, not 200 seconds, but just the lifetime goes down to 12 seconds. So of course, this is something that can be solved, these issues. And one simple solution that we could imagine is to operate in a shallow lattice and still try to suppress tunneling interactions by using Fermi statistics. So the idea is that if you load the atoms in a lattice, even though it's shallow, because there are fermions, if they are in the same quantum state, an atom cannot tunnel from one lattice size to the other because it's already occupied. So even the lattice is shallow, you cannot do tunnel because of quantum statistics. So in principle, that would be great, but the reality is that when the atoms are interrogated by the Cloc laser, then because this is an optical transition, you can see that the wavelength or the wave vector of the laser that is used to interrogate the atoms is not very small. Actually, the laser wave vector times A, being the lattice spacing, is comparable to pi. So this gives you a phase factor that is of the order of 7 pi divided by 6. And that means that when you interrogate the Cloc, then you are going to imprint different phases of the atoms. So basically, if you think as a block vector, the atoms are going to slightly rotate different angle depending on the lattice side, because the phase changes from one lattice size to the next. The atoms become distinguishable, and therefore, so this effect, that this different imprinting of the phase that I'm going to call now spin orbit coupling and will explain in the next slide, is going to make my atoms vulnerable to tunneling and therefore to collisions, and therefore in principle both interactions and spin orbit coupling are bad for clocks. So because of that, it was really important for us to understand the physics behind spin orbit coupling. So the basic idea is that let's try to understand what happens in the lattice. So if you have atoms, this is non-interacting atoms at the beginning with a dispersion relation that is the form of a cosinusoidal dispersion relation, because of course you have atoms in the lattice have this band structure. Atoms, excited and ground state atoms feel exactly the same band structure because they are in a lattice, what is called magic lattice, that makes the dispersion relation identical for the two Cloc states. You have the ground and the excited state, and in principle, they're just different by a global detuning from the laser beam. But the point is that when an atom is in the ground state and I absorb a photon and is promoted to the excited state, because it's an optical transition, it experiences a momentum kick given by the laser, by the photon that they absorb from the laser. So they start in momentum Q0, and then when they make a spin flip, they go to Q0 plus the Q laser. That means that the phase that they have is not Q0, I mean, it's changed from the original that they have here. So one way to understand or trying to manipulate or understand better or write it in a more convenient way what is happening is that instead of making the transitions non-diagonal when you have the laser, we can introduce a gauge transformation. I mean, we can shift the dispersion relation of the excited state. So now everything is diagonal, but of course, because of in principle they are changing momentum, then the laser is coupling atoms with dispersion relation to J cos Ka to a dispersion relation that is cos Ka plus phi. So there is a shift, and because there is a shift, you can see that this can be seen as a detuning, or the energy difference between the ground and excited state that now depends on the quasi-momentum of the atom. So it's for example, the shift is different here or here or here. So, but everything is diagonal. So this is the gauge transformation that I have. So the Hamiltonian for the non-interacting particles, you can map it to an effective spin two-level system, because you can see the momentum is just diagonally momentum, and the effect of the laser is introducing an effective magnetic field that has a component along the x direction given with the strength omega, and now the detuning that is now momentum dependent. That is the difference in dispersion relationship between the ground and the excited band and the global detuning from the laser. So if that's what we understood by spin orbit coupling, is the fact that the spin flips are accompanied by momentum transfer. Okay, so I'm drawing here kind of the bare states. You can imagine that if you have very strong Rabi drive, then you are going to have a mixture of dress states. So the dispersion relation is only very similar to the original one when the omega, the Rabi drive is small. For a strong Rabi drive, the eigenstates are going to be a superposition between the ground and excited state. And more visually, you can see that the eigenstates of the system, of course, are going to depend on momentum, and they're going to be associated with eigenstate pointing on the direction of the effective magnetic field that is in the x and the c plane, and the orientation of the eigenstates is going to set by by omega, the ratio between omega and the detuning, basically. So this is another way to see the spin motion locking of the atoms, and this type of spin locking is what we want to see, and that's one of the things that we want to explore in the experiment. So in order to make the system weakly interacting, the experiments were done, instead of the 3D lattice, were done in a 1D lattice. So we have an array of pancakes with the idea of releasing a little bit the confinement along the other two directions to make the gas less interacting. And so the work that I'm going to talk about has been summarized in these two papers that were published in 2017 and 2018 with a theory prediction before. So if you want more information, please refer to that. But I want to try to summarize the main findings there. So the basic idea is that, well, we want to probe this type of band of the band structure of this spectrum. And one of the first things that we did is just Rabi spectroscopy. And notice, so these are the bands. I mean, maybe this is drawn with a small Rabi drive, but you can see that these bands are going to touch or be very close in energy at a specific points in the quasi-momentum distribution, and these specific points are going to depend on the detuning, global detuning of my laser. So here they're touching here, but if I increase the detuning, they're going to touch at different points. And at some point, when my detuning is very larger than the bandwidth, then the bands are not going to touch. So basically, what we can do is we can. Let's see if I can. Okay, I cannot do. Okay, so. Yeah, so let's see. Okay, this, yeah, so the bands are going, by changing the tuning, I'm going to modify how the band touch, basically. And the basic idea here is that we probe the number of atoms. We start with the atoms in the ground state and probe the number of atoms in the excited state as a function of the detuning for different temperature of the gas. And what we see is that, well, you can see that there is no population transfer after we have the tuning that is larger by the bandwidth, because well, 2 times the bandwidth sine phi divided by 2, because after that the bands stop to touch. And when there are bands are touching, we see that we have a lot of population at some specific points. That is when the bands are just barely touching, because at this point is when we have a divergence in the density of states. We have what is called a Van Hoff singularity, and well, these were theoretical predictions, and they get just a little bit smoother as we go to hotter temperatures, but they are there. So let's see. The idea is that this Rabi spectroscopy can give us information of both the phase and the tunneling, because those enter in the width of where we see populations. So the experiments did exactly what we proposed. They start with atoms in the ground state, apply a drive, promote atoms to the excited state, and measure the atoms in the excited state. These are experimental data that are shown for different lattice depths. So the weaker the lattice depth, the larger the tunneling, and therefore the larger the width where we see a transfer of population. As you go to very, very shallow, a very deep lattice, then you can see that the bandwidth is very small, and then we see kind of a single peak. So that's the solid lines are theory, the experimental points are symbols, and you can see that we describe very well the non-interacting physics. I mean, we have to make a small correction. So if you plot the width of this structure, you can see that we can describe very well that with theory. If we correct a little bit the tunneling by some radial effect on temperature because of radial and axial coupling, but basically we can understand the single particle physics very well. Now, the other experiment that we did is trying to really look at this spin momentum coupling, or I mean, how it depends on the quasi-momentum. So for that, again, we use the capability, the laser, and in this case, we are going to take advantage of having a very narrow laser, where I'm only going to transfer the population when the ground and the excited states bands are very close to each other. So only in this case, for example, only in this region where the tuning is small, we are going to transfer the population. So we apply the pulse, a weak pulse, and then we blow up the atoms in the ground state. So for that, by doing that, you can see that we are selecting some momentum window, and this momentum window here depends on the detuning that we choose on the globe of the laser tuning. So here we choose a window of quasi-momentum close to zero that is very close to the Van Hoff singularity, for example. So we are able to transfer atoms in a specific window, but as I said, for example, we can change the window by changing the different the tuning, and that's what we have done that for example, this window or this window and so forth. And then what we did is that, well, we have atoms prepared in the excited state. And now the point is that we are going to quench omega such that the eigenstates of the system are going to point in a direction that is set by both omega and the tuning that depends on the momentum. So it's atoms with different detuning are therefore going to oscillate, do Rabi flopping along an axis that changes by changing the quasi-momentum. So that's what we did. We changed the quasi-momentum in different windows, and you can see that the Rabi drive sets different orientation with the Rabi drive. We have different rates of precession of the atoms that indicate the spin orbit locking, and that's exactly what we saw in the experiment, and that's what the symbols are the experiment, the solid lines are the theory. So very clearly, we could observe this spin orbit coupling in the system via momentum resolution. All right, so that's nice. So we can understand very well the effect of single orbit coupling, but of course, this is only the starting point because it's a non-interacting system. So perfectly, we could run the calculations and knew what was going on in the experiment. So the next step that I want to do is to try to understand interactions. So, but for that going on, let me start with another technique that is Ramsey spectroscopy. Again, start with non-interacting atoms, but with the goal of trying to translate to a many-body system. So in Ramsey spectroscopy, what we do is that we have two different pulses. So the first pulse transfer atoms from the ground to the excited state. Then we let the system evolve. And then what we want to measure is the phase accumulated and the amplitude of the transverse magnetization along the plane. And this can be done by applying a second pulse, a pi-half pulse. And then if we measure the population, the measurement at the amplitude of the Ramsey fringe, the amplitude is going to tell us information about the amplitude of the magnitude of a splash. That is how that determines the rotation of the spins in the XY plane during the free evolution. Here, total S are collective operators. That is the sum of the individual spin operators. So by doing this experiment, what we are going to do is that we are going to get information of this collective transverse magnetization of the array. So that's another way to understand what is going on. So for the non-interacting case, I have a Hamiltonian. Now the Rabi drive is gone, so I only have the momentum dependent detuning. But what it happens is that because we have fermions, we are populating all these different quasi-momentum. So each, depending of the quasi-momentum of the fermions, they're going to precess at a different rate. So the system is, even though initially I prepare all the systems along the x direction by the first pulse, a line along the x direction, very quickly, because each atom is going to precess at a different rate depending on the quasi-momentum, you can see that because this is a cosinusoidal dispersion relation, when we sum all the different rotations or precessions, you can see that we get a Bessel function, and the system is going to depolarize very quickly as a function of time. And the depolarization is going to be faster if you have larger tunneling. And exactly that's what you see. So you see, if there is no tunneling, in principle, very deep lattice, you see just some light scattering. But as you start to increase the tunneling, make shallower and shallower lattices, well, the system depolarizes very quickly. That is, of course, very bad for clocks in principle. I mean, you are losing phase coherence very quickly because of the tunneling. And now, as I said, well, the goal is to understand what happens when you have interactions. Let's try to first understand this behavior by looking at the collective spin bases, not the individual spin bases. So if we write collective states that are characterized by the total S and the projection along SC. I mean, the total S is the eigenstate of the total S squared with eigenvalues S that go from n½ to 0, n½ when you have the Dicke manifold. So basically, you start with all the atoms polarized along the x direction. But now, because this Hamiltonian is in the decoupled by basis and doesn't commute with this Hamiltonian, then the system is going to depolarize very quickly at a rate that is set by the variance of these couplings that is determined by J and the spin-orbit coupling angle. So you can see if there is no spin-orbit coupling, if phi is 0, if J is 0, we don't have that. But when you have finite, they're going to depolarize very quickly, and then the atoms are going to spread out, and the length and the coherence are going to become very short. All right, so now let's see what happens when we add interactions. That was the goal. One key advantage is that if we are going to go to a 3D lattice where interactions are really important, we cannot ignore them anymore. Then we have an additional knob to control the spin-orbit coupling that is set by the direction of the laser that is interrogating the atoms. Let me explain what I mean a little bit better. So what we're going to do, or what we're proposing to do, is that not explore the 3D geometry, all the directions, but make the lattice very deep along the C direction. So basically restrict the tunneling only along the XY plane. And now, because what matters is the projection of the phase that the atoms acquire in the plane of motion, then, well, you have the tunneling, the interaction, and we have the spin-orbit coupling drive, but now we can orient the spin-orbit coupling drive such that we can control the projection of the laser on the XY plane by changing the angle at which the clock vector, the k vector of the clock is oriented. So, of course, the magnitude of k times a is 7 pi divided by 6, but now we have we can weight it by sine theta. So basically, you can see if the laser is completely perpendicular to the plane, phi is 0, and we don't have any spin-orbit coupling. Whereas if we make the laser to be, for example, almost 60 degrees, we can have the maximum phase that is pi. So we can now have a knob to control the spin-orbit coupling. That is important. So let's start by trying to understand the effect of the interactions in one specific regime where we believe the dynamics is simpler, that is when the lattice is relatively weak and the interactions are not very important. But in this case, still quasi-momentum states that are the single particle eigenstates are good eigenstates. And then what we're going to treat interactions in a perturbative way. And the way that we can treat interactions in a perturbative way, well, I'm writing the Hubbard model now, not in position, but in quasi-momentum, where for the kinetic energy, we have the difference in dispersion relation, we have the drive, and then we have the interactions. Now, the point is that if I'm going to work in the regime when U is weak compared to J, or whether not relative weak, so below 5, I want to make the spin orbit coupling small. That's the regime where I know how to do I have a valid perturbation theory. And the perturbation theory corresponds to assuming that the interactions are not strong to make my atoms change quasi-momentum because it causes single particle energy. So basically, I'm going to operate in the regime when there are no momentum changing collisions, in what is called in collisionless regime. And this is accomplished when you have a k equal to 0 or k equal to a q plus minus p. This is the interaction Hamiltonian, where you have an atom with momentum p colliding with an atom in momentum q, and in principle you can scatter with atom in momentum p plus q and q minus k. But we can see, for example, if I make k to 0, then the atoms are not changing the momentum. So basically, we are trying to operate in this regime, and if I'm going to go to the lattice in momentum space, what is happening is that interactions, what can do is that not changing momentum, but instead what they can do is introduce some spin flips. The atoms are frozen in this momentum eigenstates, but they can switch momentum, they can switch spin from up to down because this doesn't cost as much energy as changing speed. So in this case, you can see that the atoms are delocalized now in momentum basis. The interactions therefore are fully long range, as you could see before. I mean, there is no, in momentum basis, there is no coupling constants. Remember, in this Hamiltonian that I have here, I have U divided by B. That is all to all. Here you can see that is all to all. So then when we go and write the Hamiltonian in this, assuming this collisionless approximation, that there is no mode changing collisions, then my Hamiltonian becomes an all-to-all spin model. When I have beside the single particle terms, I have a term that is proportional to S dot S. And this S dot S, what it does is opens an energy gap between the S equal to n-half manifold, that is where I start my atoms, and the next manifold that is spin S n-half minus 1, and the gap is proportional to UN divided by B. So basically, it's proportional to U, and if there is if B is the volume of the gas, so B divided by N is going to be the filling fraction. So it's going to be a gap that is kind of the order of the U times the filling fraction here, B, N divided by B. So it's but if this gap is larger than the inhomogeneity introduced by delta B, then you are protecting the gas against dephasing, and that's something that that is very useful because we can protect the systems against depolarization by doing this gap protection. So let me emphasize that this gap protection is not new. Actually, the model that I've just described, where you have a single particle term that is inhomogeneous and some term that is the form of collective S dot S. Well, this is the Hamiltonian that people use to model BCS superconductors under what is called the Anderson mapping, where if you have a Cooper pair or you have an empty site, you can describe these two states as an effective spin up and down, very close to the superconducting transition. Only doubly occupied sites, Cooper pairs or vacant states are the relevant in your Hilbert space. And when you write the interaction Hamiltonian, you get exactly the same Hamiltonian that I'm describing before. You can define another parameter that is exactly S minus, and the magnitude of S minus is exactly the contrast that we are measuring via Ramsey spectroscopy. And the point here that I want to emphasize is that condensed matter theories have looked at this Hamiltonian before. They have seen that this Hamiltonian is fully integrable. It belongs to some type of Richardson-Godin model, and they have been able to define exact solutions of the mean field dynamics via what they call lax construction. So I don't going to elaborate this too much, but they give us a recipe to actually determine what is the non-equilibrium dynamics of atoms or systems described by this Hamiltonian, that you have a collective S dot S term and something that is inhomogeneous. They have been using, for example, to describe different phases in superconductors. There is a lot of literature on that. And what we did is just to take this literature and construct the dynamical phase diagram of our system. And it has two different phases. A phase is where single particle wins for weakly interactions, and the magnetization completely disappears after very short times. And another phase that we call phase 2, where the magnetization becomes stable, saturates, and the system remains polarized, with a transverse magnetization that is finite, and therefore retains its phase coherence. So there is a critical point that is set by the tunneling and the spin-orbit coupling angle. So we have these two behaviors. So the idea is that we want to go operate in this regime for the clocks, where spin-orbit coupling is not bad, but interactions and spin-orbit coupling cooperate to protect the coherence. This is not new, of course. They have been seen in rubidium atoms. These are bosonic systems. In Hanover, for example, they call it a identical spin rotation effect. And they were seeing that interactions can protect the systems against dephasing. We saw these type of similar systems, for example, in a cavity and in James Thompson's group at Gila, and Monica in Stanford, she was able also to look at, observe this type of gap protection in a cavity system. It's not exactly the same, but it's related to time crystals, that interactions can prolong the coherence time of a system. And these type of effects, have been in direct connections with dynamical phase transition, because you see two different phases and similar behavior we were able to see, for example, in fermionic atoms in a trap. So what I'm saying is that these transitions have been seen before. The fact that interactions can protect the systems against dephasing and favor coherence. That's great. In principle, it's very useful for the clock. But one of the biggest advantages that we have now is that the clock can interrogate the atoms for a very long time. And so far, I have to mention that all the phase diagram that discussed before and all of these physics that have been seen in prior experiments is mainly mean field-like, purely mean field. And everything can be described, mean field describes things well at short times. But what happens is when we start actually solving the dynamics for the Hubbard model, and started to see what happens at long times. This is the contrast as a function of time for different interactions. Here we see that the system at the mean field solutions predict, for example, for weak interactions that the magnetization decay. For strong interactions, the magnetization remains stable. But when we look and solve for the exact solution, then we see that even though the mean field is telling us that the magnetization should be stable and not decay, we start to see it decay. So the question is, what happens when in this system where it should be stable? And of course, the reasons is that beyond mean field effects start to kick in the behavior. So now I'm going to enter the part where I'm going to start discussing beyond mean field effects. So far, it has been non-interacting or mean field. So maybe this could be a good point to start questions for all the prior part. And I will continue with the beyond mean field effects in the rest of the talk.
Okay. So William, you have a question. Can you unmute yourself? Let's see.
About where you have this phase transition to a situation where you have effective non-zero magnetization that corresponds to the locking of the phase that is suppressing the decoherence. The magnetization is not 100%, so that means that there is a portion of the sample that is not phase locked. And what I'm wondering is whether that portion, if it's not completely symmetric, you could imagine that it might pull the clock transition. So is there any problem there?
Yes, so in principle, you are talking about mean field shifts that you cause. Yes. Well, let's look at this. So depends what we want to see. So the Hamiltonian is J S dot S, is completely fully symmetric. So in principle, there is not, because there is SU2 symmetric, there is not a net mean field shift that, for example, would give you an SC square Hamiltonian. Yes, in principle, it's not giving you kind of the same type of density shifts that we saw before. On the other, I mean, this term, so the phase shifts, if you are assigned to see in some degree this term, and this is going, you are anticipating my next slides, Bill. So if the system is going to be actually projected to the Dicke manifold, you can see that the mean of these interactions are going to introduce a net density shift, because it's an effective global detuning when you project this onto the mean value of this quantity. So there is going to be a density shift that is set by the mean value of these quantities. But I think it's not as bad. I mean, there is, but always larger. I mean, for example, if we have the average of these quantities to zero, that is happening when you are populating all your band, then the average is zero, so there is no net density shift. So the advantage here is that we have really S.S interactions, and I mean, they don't cause the type of mean field shift that we would be worried about. Does that make sense?
Yeah. Now, since you're on this slide, the other question that I had was, when this system is effectively simulating a BCS superconductor, how should I understand what the physics is that is analogous to the electron-phonon interaction?
Yeah, so this is, I think we are talking about here, after eliminating the photons, we have an interaction between the electrons. So the Hamiltonian that we start is already C-Dagger is exactly like the Hamiltonian that we have before. That you adiabatically eliminate the phonons, and the phonons generate an interaction between the electrons. This step is already done. Okay. And then you are going to get an interaction that is C-Dagger here. You are going to have an interaction that is CC, C-Dagger after the elimination. And this destroys two atoms. That destroy the Cooper pair and create a Cooper pair. That's the Hamiltonian that describes BCS superconductivity, and we start from that after eliminating the phonons. Does that make sense?
Yeah. Okay, thanks.
All right, do we have any more questions? I don't see anything in the chat, and I don't see anything in the YouTube, so I think you should be okay to continue.
Okay, great. So now let me start to understand a little bit the beyond mean field effects that we can explore now, in principle, in the Cloc. So the basic idea is that we want to be in the gap protected phase, where basically we want to live in the Dicke manifold. So the first effect that this gap protection does is to project the spin orbit Hamiltonian into the Dicke manifold. So when you project, so we have the S.S interaction, but when now you project this term into the Dicke manifold, you are going to have a collective SC times B average, that is B average, the sum of these single particle BQ terms, effective fields. This is to first order, but you can see that now we can go to higher orders that might show up at longer times in the dynamics. And the effect is that, okay, we can have virtual transitions between the fully symmetric state, the spin wave state, and then this is going to happen, of course, via the delta V, but it's going to be only virtual, so we can apply second order perturbation theory. And because everything is projected in the Dicke manifold, when I go to second order, I'm going to have an SC square Hamiltonian. And then what happened is that I'm going to get an effective interactions. The strength of this SC square is going to be the variance of the coupling constant divided by the gap that is of order U. So basically, we are going to get a Hamiltonian that is fully collective, even though we are talking about fermions, with with a small amplitude of KF that's set by the spin orbit coupling angle. So when we look at this effective Hamiltonian, then it's really encouraging, because actually this is one-axis twisting Hamiltonian of the form SC squared is what people have thought to generate some type of entanglement that is useful for metrology, that is spin squeezing. Basically what happens is that if you have the quantum noise of the atoms, then initially, if they are not correlated, then they are going to have a distribution that is spherical, perpendicular to the block vector. But at some point, if you are able to stretch this noise and make it narrow along one direction compared to the other, then we can be, and this type of stretching is done by this spin orbit coupling model that you can see that there is a rotation that depends on a C. This is at the mean field level, but actually this is happening, that the noise is stretched and has a smaller variance along some direction. This is characterized by the spin squeezing parameter that also is a witness of entanglement if we actually are able to if this parameter is smaller than 1. So any anisotropy that you get in the noise can be is a witness of entanglement. So basically, that's what we are going to do. We are going to use two bad effects that are interaction and spin orbit coupling. The worst thing that you could imagine for clocks, we are going to harness them to make a spin squeezing the lattice clock. So this is just summarized in this recent paper that we have on that. And let me explain a little bit better. So I don't know, but for us, the idea that the Hubbard model that describes strongly interacting electrons behaves like an all-to-all Ising model is really shocking. I mean, it's really weird. And so, of course, the first thing that we wanted to do is to do the MRG calculations to show us, is that case, the case is really the Fermi-Hubbard model behaving as an all-to-all Hamiltonian? Well, the answer is yes. This is the squeezing. I mean, this shadow region is the region where we have what predicted by the one-axis twisting Hamiltonian. This is independent of the interactions. It's just set by the form of the Hamiltonian and the number of atoms. And the Fermi-Hubbard calculations and the spin model are shown by the blue and the dashed line. And you see that when you do need filling for small spin orbit coupling angles, it agrees very well with the Hubbard model, very well. When we go to lower fillings, actually it's not that well, but there is a broad parameter regime where those agree. So the squeezing is 0. Of course, when you have no gap protection, it's only present when you have gap protection, but there is agreement between the Hubbard model and the all-to-all Ising model. So we are making fermions behave like kind of bosons in some degree. Of course, in principle, we can get a lot of, if we have 10 to the 4 atoms, we could get a large amount of spin squeezing, but still current experiments are limited to 12 seconds coherence time. And therefore, well, it's not going, the spin squeezing is going to be set by how long we can go up to this time. And this is a plot of the achievable spin squeezing that we predict for different lattice sites from 20 to 200. This is one direction of the lattice, so you have L squared for the number of atoms, and we see that there is a significant region of the system where we can get like between 12 and 13 spin squeezing. Of course, I'm trying to compare with all this table is overwhelming a little bit with all the spin squeezing that have been done in colatoms, and you can see that, well, in principle, we should be operating in this region when between 10 and 100 atoms we have between like 12 dB. That of course is not the record of spin squeezing done in cavities. It is here, but I want to emphasize that if we were able to implement this spin squeezing, it's going to be implementing the best in a metrological useful system. It's not implemented in something that is not useful for metrology. So we are hoping to open a window to actually use many body effects to improve the operation of an optical lattice clock. Of course, the experiment has not been done. It's working on that, but hopefully we can, I mean, this is a recipe that you could achieve a spin squeezing without the need of, for example, adding a cavity that might introduce further complications in the clock. So in the last 8 minutes, I think that I would like, I mean, I just wanted to go and do a brief summary of, I have done a description of the weakly interacting regime. We know that the Hubbard model is much complicated like that. I mean, the phase diagram of the Hubbard model is not well known. It's supposed to describe the behavior of ITC. It's not well understood yet, but there is a regime that we understand very well. That is the regime when there is no doping, where we have super exchange interactions. And in this case, there is no motion, but only a spin Hamiltonian that can explain the antiferromagnetic behavior that you see in the Hubbard model. This happens through the so-called super exchange interactions that in some way they're easy to understand. If you have something that is at one atom per side, and if you have a tunneling and strong interactions, an atom can tunnel to one side, experience and feel the other atom, feel that it's too much energy, so it goes back, it's virtual process again, and an effect, you have a Hamiltonian that is J squared divided by U, that is of the form S dot S. This is fully symmetric, as you can see, it's SU2. And what we have been studying is what is the effect of a spin-orbit coupling in this regime. And what we find is that it modifies the spin-orbit model, the spin model that you have, make it more richer, and actually the dynamics even faster. That's very important. So my student Michael Mamaev have been able to derive the Hamiltonian when you have both a spin-orbit coupling in the Hubbard model, and it transformed the S dot S Hamiltonian, the Heisenberg model, into what we call an XXZ model that has some coupling constant that you can see has the denominator of U squared divided by omega squared. So this can be make it small and therefore enhance the timescales that you need to see super exchange interactions. They have the anisotropic exchange term that is called the Taylor-Maria interaction term that now arise if we have a spin orbit coupling, and of course the drive. So there is a lot of parameters that we can use to manipulate this system. And what we have done is trying to understand the different phases. I mean, this is not a phase diagram, but the different behaviors that you could explore using a spin orbit coupling in the super exchange regime. So basically, this is the Rabi drive, and this is the spin orbit coupling angle. And we are going to characterize the Hamiltonian with different type of behaviors that, I mean, the Hamiltonian is the complex beast that I showed you before, but there is a broad parameter regime where the physics simplifies. So for example, here, when you have a small flux, that is the behavior that I told you before, we can make the Hubbard model, even in the strong interacting regime, in the superstructured regime, behave like a one-axis twisting Hamiltonian, as explained before, where the coherence barely decay, the contrast almost remains equal to 1, there is a point here. And the dynamics can be faster or slower, depends on when I add the Rabi drive. I have this regime where there is no drive, but still I can have large spin orbit coupling angle where we have the Heisenberg by class twist Hamiltonian, and we have some chiral behavior. And the most interesting part is that I can have also Ising type behavior. If I go to a flux that is of order pi, then I can actually tune my system such that I can generate Ising terms. And we have shown, unfortunately, I will not have time to tell you today, but if we operate in this regime, what we can do is that we can engineer cluster states. We have a protocol that if you operate in this regime, we can engineer a sigma C Hamiltonian that generate cluster states. We can also operate here a little at a strong trap, and we can use this spin orbit coupling to generate cat states. And this is a protocol that we described in a recent PRL, and where we can go in this regime when omega is equal to U, and we can have very interesting quantum cell entropic localization. I mean, this becomes a little bit complicated, but what I wanted to show you here is that there is a slew of possibilities that we want to explore, that we can explore when we combine the Hubbard model with the spin orbit coupling. And well, unfortunately, I don't think I will have time to tell you about this. If you have questions about how we are going to do about this different generation of CAD states and so forth, I'm happy to discuss it in questions. But with that, let me see if I can go 1 second. 1 second, sorry. I'm going to go my, okay, let's see. Yes, so let me go and here and let's, let me go with the summary. So as I said, if you have questions about these different ways to generate entanglement, I'm happy to talk. But hopefully in this talk, I have told you that the spin-orbit coupling occurs naturally in an optical lattice clock. And this we have you can find information of what I discussed here in these papers. The second important message that I hope to transmit is that driven many-body and interacting non-equilibrium systems can be used to prolong spin coherence and generate entanglement. The surprising part is that the Hubbard model, even though it's so complicated, can behave at a one-axis twisting Hamiltonian. That was very surprising. And the hope is that we are now at the very soon to operate in a new regime of many-body interacting spin-orbit coupling fermions, where we can use these type of couplings to push the clock and not only generate a spin squeezing, as I discussed before, but maybe we could generate cluster states and cat states in the near-term future. And so with that, and just let me finish and say that I really think that there is a bright vista ahead, and maybe with the marriage between many-body physics and very precise clocks, we can bring these clocks at the level to make quantum simulation, quantum computers, and really advanced quantum technologies. And with that, let me thank you for your attention, and I can have more questions.
Great, thank you. So yeah, open the floor to questions. If you have any, just raise your hand or type it in the chat, and I will read them. Okay. Well, it was a wonderful talk. Thank you so much for joining us today, everybody. And thank you so much, Anna, for giving this wonderful talk. And we will see you all in the next seminar. Thank you. Signing off.
Okay, thanks.
All right, I will finish